polynomial equations. Our objectives: use the rational zero theorem to find rational zeros, use the factor theorem to solve a polynomial equation, use synthetic division to find the zeros of a polynomial, use the fundamental theorem of algebra to find complex zeros of a polynomial function, and use the linear factorization theorem to find polynomials with given zeros. The factor theorem. The factor theorem states that k is a zero of f of x if and only if x minus k is a factor of f of x. When we look at a theorem like this, we have if and only if in the middle. It means that we can use this theorem forwards and backwards. So this also means k is a zero of f of x if x minus k is a factor of f of x, or x minus k is a factor of f of x if k is a zero of f of x. So in this way we can see factors and zeros are closely related, and we can use them to help us find the information that we need for polynomials. So let's fill in this table. Here we have a factor of x minus 5. Well, I know by this theorem if x minus 5 is a factor, then k is the zero. So what is the zero? X minus 5, 5 is the zero. So 5 is your zero. Now if I have a zero of negative 3, then I know that x minus a negative 3 is going to be my factor. Here I have a factor of x minus 2 minus 3i. So we're thinking about what number was subtracted from x. That number would be 2 plus 3i. If I have a zero of 7 minus 5i, then the factor is going to be x minus 7 plus the 5i. Remember, we're taking x minus the entire zero. So x minus 7 plus 5i. If my zero is 3 minus the square root of 7, then the factor will be x minus 3 plus the square root of 7. Here, let's use the factor theorem to decide whether x plus 1 is a factor of f of x equals 2x plus 4 plus x cubed minus 9x squared minus 13x minus 5. So the factor theorem says that x plus 1 is going to be a factor if negative 1 is a zero. How would we find out if negative 1 is a zero? Well, we would find out by going ahead and running this through our synthetic division process. So I have 2, 1, negative 9, negative 13, and negative 5. We carry down the 2, so we have a number to start with, and then multiply up, combine down. Multiply up, combine down. Multiply up, combine down, multiply up, and combine down. There is our remainder. The remainder is 0. That tells us that negative 1 is a zero of the polynomial. So by the factor theorem, x plus 1 is a factor of f of x because negative 1 is a zero of f of x. Multiplicity. The multiplicity of a zero is the number of times its factor appears in factored form. So let's determine the multiplicity of negative 1 as a zero of f of x, the function that we just worked on. We've already determined that negative 1 was a 0. So what we'll do is write this polynomial in partially factored form. X plus 1 we know is a factor. We've taken out a factor of x plus 1, so the quotient is now 2x cubed minus x squared minus 8x minus 5. Now, when I look at this, I can go ahead and see if negative 1 might also be a 0 of this polynomial, the quotient that's left over. So let's run our synthetic division again. I'm going to put in a negative 1 through the process, carry down the 2 so we have a number to start with. 2 times negative 1 is negative 2. Negative 1 and negative 2 is negative 3. Negative 3 times negative 1 is positive 3. Negative 8 and 3 is negative 5. Negative 5 and negative 1 is 5. Negative 5 and 5 is 0. So we see that negative 1 is, again, a 0. Let's take just a moment and see if we can go ahead and write this in partially factored form. X plus 1 is now a factor twice. So we have a x plus 1 quantity squared, and the quotient after our last division is going to be 2x squared minus 3x minus 5. All right, now let's see if we can get negative 1 as a 0 one more time. We're going to use the quotient of 2, negative 3, and negative 5 in our synthetic division table, and we'll push a negative 1 through there again. 2 times negative 1 is negative 2. Negative 3 and negative 2 is a negative 5. Negative 5 times negative 1 is 5. And negative 5 plus 5 is 0. So it looks like it has worked one more time. Again, we can factor a little further. This is now x plus 1 cubed. And we're left with a 2x minus 5 as our last factor. For us, this means that the multiplicity of negative 1 is 3. So we'll state negative 1 is a 0 of multiplicity (3). The fundamental theorem of algebra. If f of x is a polynomial of degree n greater than 0, then f of x has at least one complex 0. If f of x is a polynomial of degree n greater than 0 and a is a non-zero number, then f of x has exactly n linear factors, and the polynomial can be written as f of x equals a times x minus c sub 1 times x minus c sub 2 x minus c sub n, where c sub 1, c sub 2, c sub n are complex numbers. Therefore, f of x has n roots if we allow for multiplicities. This means that if we have a fifth degree polynomial, we will have 5 roots, or 5 zeros, if we count the multiplicities. So let's use this for factoring. Let's place our f of x in completely factored form. We left off with the f of x as x plus 1 quantity cubed times 2x minus 5. Now the fundamental theorem of algebra that we just went over says that we can factor this down to linear factors, and every x is a plain x in those factors. We don't have that here. We have a 2 in front of our x. So what we can do is factor that 2 out. Let's go ahead and write it first like this. I'm going to factor out the 2 from this 2x minus 5. If I do that, I'll have x minus 5 halves. Then it looks just a little nicer if we go ahead and put the 2 in front. 2 is our a. Now, it won't always be the case that we are handed a number that is a 0 of a polynomial. So we need to find a way to be able to test some numbers that could be good possibilities. This is where the rational roots theorem comes in. The rational roots theorem says if n over d is a rational 0 of a polynomial, n is a factor of the constant term, and d is a factor of the lead coefficient. So let's use the rational roots theorem on our next problem. Find all the zeros of f of x and place in completely factored form. F of x equals 2x to the fourth plus 5x cubed minus 5x squared minus 5x plus 3. They've not given us any hints for values of k to try, so let's go ahead and make a list. The rational roots theorem says that all of our factors that are rational will be of the form factors of the constant term, so that'd be plus or minus 1 and 3, divided by factors of the lead coefficient. So that is plus minus 1 and 2. Let's go ahead and settle this out to some simplified terms. 1 divided by 1 is 1. 3 divided by 1 is 3. 1 divided by 2 is 1/2. And 3 divided by 2 is 3/2. So we have the positive and negative of all of these numbers that could be rational zeros of the polynomial. If we have rational zeros, it's going to be one of these, and 8 possibilities. Let's go ahead and start testing to see which ones are zeros. We do that by synthetic division. I like to start with 1. I'm setting up my synthetic division table, and we'll start that process. Carry down the 2. 2 times 1 is 2. 5 and 2 is 7. 7 times 1 is 7. Negative 5 and 7 is 2. 2 times 1 is 2. Negative 5 and 2 is negative 3. Negative 3 times 1 is negative 3. 3 and negative 3 is 0. So I see that 1 is a 0. I can go ahead and partially factor this. It's now x minus 1 times 2x cubed plus 7x squared plus 2x minus 3. Now, 1 might be a 0 with multiplicity. So let's go ahead and take 2, 7, 2, negative 3, our quotient, and see if we can get another 1 to be a 0 of that polynomial. Carry down the 2. 1 times 2 is 2. 7 and 2 is 9. 1 times 9 is 9. 2 and 9 is 11. 1 times 11 is 11. And negative 3 and 11 is 8. So 1 is not a 0. And in fact, I see that all of my numbers in this row containing the quotient and the remainder are positive numbers, and I've put a positive number through the synthetic division table. There's another theorem that we won't look at now, but it says that if this happens, then 1 is an upper bound for that polynomial. It means that there are no numbers that are larger that are going to work. So at this time, I'm not going to bother with dividing by 3. I'll go ahead with this process and start with, let's probably start some negative numbers. Let's try with -1. Carry down the 2. 2 times -1 is -2. 7 and -2 is 5. 5 times -1 is -5. 2 and -5 is -3. -3 times -1 is 3. And -3 and 3 is 0. So we found another 0. That means I can come up here and factor this now as x minus 1 times x minus -1 times the quotient of 2x squared plus 5x minus 3. Well, now that I have it down to a quadratic, I can try and factor this. So I've got an x minus 1 times an x plus 1 and 2x and x. Let's try a 3 and a -1. That would give me my positive 5x that I need in the middle and my -3 constant term. We're so close to being finished, but this needs to not be there. Let's go ahead and factor out that 2. I'm going to put it out in front of the entire polynomial factorization. So I have an x minus 1, an x plus 1, and here is where I factored out the 2. So this would be x minus 1/2. The 2 was pulled out of that one factor, and x plus 3. I now have my polynomial completely factored, and we need to list our zeros nicely. I have zeros of 1, -1, 1/2, and -3. Now we did not find these by synthetic division. We found them by factoring and setting each of those factors equal to 0. The conjugate root theorem. If a polynomial function f has real coefficients and a complex 0 of the form a plus bi, then the complex conjugate of the 0, a minus bi, is also a 0. So for us, this means that if 1 plus the square root of 2 is a 0, then 1 minus the square root of 2 is also a 0. Then the factors would be x minus all of this 1 plus square root 2. So it would be x minus 1 minus square root of 2. And x minus all of this would be x minus 1 plus the square root of 2. Now, if 2 minus 3i is a 0, then 2 plus 3i is also a 0. And those factors would be x minus 2 plus 3i and x minus 2 minus 3i. If -5i is a 0, what would be the conjugate? Well, remember, as a complex number in a plus bi form, we have 0 minus 5i. So the conjugate would be 0 plus 5i, or just 5i. Now, the factors of that would be x minus the -5i and x minus 5i. Let's find a polynomial of minimum degree with real coefficients given that -3 and 2 minus I are zeros. and the y-intercept is at 0, 5. Well, to start to building this polynomial, we'll have y equals some lead coefficient a. I know negative 3 is a 0, so that means x plus 3 is a factor. I know that 2 minus I is a 0, so x minus 2 plus I is that factor. Now we also know that we have only real coefficients. If we were to multiply these together, we would end up with an I in our polynomial. That's not allowed here. So we need real coefficients. That means our conjugate zeros theorem comes into play. I know that if 2 minus I is a 0, then its complex conjugate 2 plus I is also a 0. And the factor that makes is going to be x minus I. Now we can go ahead and multiply this together, and then we'll work at making sure that our y-intercept is at 0, 5. Y equals a times x plus 3 times, now I want to call to your attention here, we have a unique situation where we have a way to do this a little bit more quickly. If I can look at this as an x minus 2 plus I and an x minus 2 minus I see that I have these conjugate pairs to multiply together. That really does help us out, because when I multiply them together, they're conjugates. This is like an x plus y and an x minus y. And when you multiply those conjugate pairs together, the middle signs drop out and you get a difference of squares. So I'm going to use that fact to help me to multiply this a little more quickly. I have x minus 2 times x minus 2 is going to be x squared minus 4x plus 4, and a minus I times I is I squared, which is negative 1. So I'm subtracting a negative 1, making that a plus 1. Let's simplify just a little bit inside that second set of parentheses. I now know that that is x squared minus 4x plus 5. Now I can go ahead and multiply the binomial and trinomial. This is going to give me x cubed minus 4x squared plus 5x plus 3x squared minus 12x plus 15. Let's simplify a little more. This is an x cubed minus x squared minus 7x plus 15. Now my job is to make sure that I have the right numeric value in front that's going to give me a y-intercept of 0, 5. Well, a y-intercept of 0, 5 means that y is 5 when x is 0. So I can replace all of these x's with 0, and it leaves me with just a 15. Dividing both sides by 15, I get an a of 1/3. So y is 1/3 times x cubed minus x squared minus 7x plus 15. Once more, simplify again. I have 1/3 x cubed minus 1/3 x squared minus 7/3 x plus 5. Just one more for practice. Let's factor x cubed plus 3x squared minus 12x minus 18 and find its zeros. So we're going to start out by synthetic division. And how do we know what numbers to try? Remember, the possible rational zeros are going to be of the form plus or minus factors of the constant term divided by factors of the leading coefficient. So we'll have plus or minus 1, 2, 3, 6, 9, and 18. Let's put our coefficients in here and start our synthetic division to find zeros. Let's start with 1. 1 times 1, 1. 3 and 1 is 4. 1 times 4 is 4. Minus 12 is negative 8. 1 times negative 8 is negative 8, and we get a negative 26. That's not going to work for us. So let's move to the next possibility. 2. 1 times 2 is 2. 3 and 2 is 5. 5 times 2 is 10. 10 and negative 12 is negative 2. 2 times negative 2 is negative 4. Negative 4 and negative 18 is negative 22. Not a zero. So let's move to the next possibility. That would be 3. Carry down the 1. 1 times 3 is 3. 3 and 3 is 6. 3 times 6 is 18. Negative 12 and 18 is 6. 3 times 6 is 18. And negative 18 and 18 is 0. Alright, so I now have this factored to x minus 3 times x squared plus 6x plus 6. Now, I don't have to continue with the synthetic division process to find zeros anymore. I have this down to a quadratic. So I can try to factor it just with usual methods, except that it does not factor with those usual methods. So how do we find the factors? We know from the fundamental theorem of algebra that everything will factor down to linear factors, so we can't leave this squared factor. Well, let's go ahead and use the quadratic formula. If I can find the zeros of this, then I can turn those zeros into factors. So x is negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So x is negative 6 plus or minus the square root of 12 over 2, which is negative 6 plus or minus 2 square roots of 3 over 2. So x is negative 3 plus or minus square root of 3. I can now put this in completely factored form. In factored form, we have x minus 3, x plus 3 minus square root of 3, and x plus 3 plus square root of 3. And my zeros, nicely listed in one place, are 3, negative 3 plus square root 3, and negative 3 minus the square root of 3.